All right, we're back. Welcome back, everyone. If you're watching on YouTube, thanks for watching. Keep watching the series. We're back with more coding content today, and we're gonna keep going on the grad school project, right? The wireless channel generative model. And I think last time where we left off, we sort of had this full training pipeline, which actually trains the diffusion model on some sort of wireless channels. And let's give that a go. I think it's just UV run-m. What is the module called? Is it DiSco or MIMO? Oh, it's MIMO, okay. MIMO.train. And this should work. It should train a model on the GPU with everything. Okay, there we go. So we have a loss function. We have actually a diffusion model. We have a UNet from the diffusers package, which is not little. It's over here in get model, right? The loss is kind of going down, but then it's kind of stalling too. And today we gotta do a really big thing. Today we are going to generate some training data or figure out what we want to train this thing on. Okay, so we can stop this. And because one issue we said is we don't have realistic training data, this loss actually cannot go down, because if we remember, let's go to the drawing board. But last time we sort of explained how these diffusion models actually work. There's a difference between training and inference or sampling from them, right? So they're basically denoisers during training, right? We add some noise to the data, and then we predict the negative noise back, which is pretty much the same as predicting the data. So nothing groundbreaking there. But when we use them, we start from pure noise and we sort of create data from it, which kind of seems magical, but it turns out that if you train a denoiser at many noise levels, okay, which is something else that's important in the training loop, the noise level itself is randomized, okay? And we'll have to talk about that. I don't think or maybe we did a basic random uniform noise power for now. But there are some choices there on on which noise levels to train, or how to distribute the sampling of noise, or what is the distribution of noise level training power. But given a denoiser, given a sort of this entity, which is a deep neural network that can denoise or predict the noise from multiple levels of data plus noise, each with different coefficients, we can sort of magically get from 1 times noise plus 0 times data, so pure noise, no structure. We can get to 0 times noise plus 1 times data, which is pure data without noise, right? So this is what you call, we can generate synthetic data, okay? And the problem is, what are we training on though? Because right now, noise is Gaussian, right? Random, in our case, complex valued. It turns out that right now our micro training, or our training pipeline, also trains on Gaussian data. So then it's sort of perfectly indistinguishable from noise, right? It's like we're trying to purify noise from noise. That doesn't work mathematically, so that's why the loss is stalling, okay? But let's talk a bit about what we really want to train on, okay? And this is a good chance to talk about what is a wireless channel. Okay, so very, very high level. Well, very high level. The wireless channel is a matrix in our case, okay? Or now you may have noticed MIMO is in the title of the project. What the heck is, and we said what it is. It's multiple input, multiple output. We're gonna explain and finally understand what the heck this means, okay? So at the very highest level, a MIMO channel is the medium, or between the transmission, it characterizes the transmission medium between a number of transmitters and a number of receivers, possibly and likely different, okay? So let's say on this side I have ... okay? And I also have ... here. Okay? And let's say I have the first transmitter here, the second one here, and we're gonna denote, we're gonna use NT for number of total transmitters, and guess what, we're gonna use NR for number of total receivers. Okay? So what does it mean it characterizes the transmission medium? Well, we're gonna simulate these today, but the models are a bit more complicated. But I think a good analogy that I like to make is that this is similar to NT speakers speaking at the same time over each other. And what do NR listeners placed at different places hear? And we're talking about people here, right? So the most basic channel, which is still technically MIMO, okay? So this is generic, right? Now, if we take the most basic channel, what is it? It's a 1x1 wireless channel, okay? Well, this one's really easy because it has one transmitter and one receiver. Okay, so then we can say, let's mark these, we can call these transmitters. And then we can also call these receivers. Okay, so then the most basic channel is a 1x1 wireless channel. Now, what really happens inside this box? Well, even inside this box, there is a channel coefficient. Think of it this way. Imagine just one person is talking to just another person, okay? So somebody is talking to you and there's nobody else around either to talk or to listen, okay? It still matters how far apart, how far away from each other you are, and it still matters in what kind of room you are that may echo. And this is exactly how wireless propagation looks like, more or less, right? Because if we have this transmitter and this receiver, there's sort of a direct signal path between them, okay? And let's call this, now what happens, even this, it has a coefficient, right? So we can call this H direct, okay? But if there are even walls between them, there are still bounces of the signal, even though it's still, again, it's just one speaker and one listener, right? So I can get something like this. And collectively, let's denote these as H path 1 and H path 2, with the assumption that they also encode information about the bounce itself. Now, wireless models are, so this wireless channels models, they will simulate this behavior, right? Now, what happens is, at the transmitter though, they still hear the same sound. So there's sort of a summation operation here, which is sort of fundamental. Because this is, well, in nature, you would call this superposition, right? Because even if one person is talking to you, there we go, we can do it like this. Okay, so ultimately what happens is there's also a delay associated with each of these channels, right? So there's a delay too. And let's call these better. Let's call them HP2. Let's call it H path 2. Can I use underscore? No, I cannot use it. H direct, okay. Path 2 and H path 2 delay 1. Okay, so then what happens is I can characterize the signal in time as a function of time, okay? So if this person says something at time t, and we're going to use xt, this person receives something else at yt, at time t, which is the signal y at time t. And now you can see why the delays matter, because the direct path makes its way faster. And this, you know this from caves, like echoes are usually, not usually, always delayed by the laws of physics, right? Like an echo cannot be faster than the direct path, right? So then we have the basic channel equation for a 1 times 1 channel, which looks something like, what's it gonna look like? Y of t is h of t times x of t plus n plus noise. There's also Gaussian noise, which is very, very important, right? This is why, because there's always, for speaking, this is background noise. At the very worst, it's sort of even, I don't really know much about how human brains work, but I'm pretty sure we always hear a faint amount of noise, even just because of the structure of our ears, and because we have tiny hairs in there, and like any air current produces some noise. It's not the same. In wireless, it's actually Gaussian noise from the circuitry of the receiver. That's why I made the ear analogy, because for humans, our receiver circuit is our ear. But yeah, so now the question is, how do I estimate H? Okay, so, well, there's two questions, right? So we want to generate wireless channels. We want to train a generative model for them, and then we want to use it to estimate channels. Actually, okay, before that, let's look at another channel at a 1 times 2. No, a 2 times 1 wireless channel, okay? This is a bit more complicated now. Well, not really. It's still an equation. I shouldn't say that, but so what do we have here? We're gonna have 2 transmitters and 1 receiver. Now, in real life, this is very hard. It's like trying to hear 2 people speak about something at the same time, simultaneously. So this picture gets perfectly replicated, except now there's even more superposition on that same receiver, right? So then we can call this H1, the channel from the first user to the receiver, okay? Which has a direct path. It has its own delays, but this plus now, there is a plus here, but then there's also a way bigger plus, because all this gets replicated to the second transmitter, and now he speaks X1, and this person speaks X2, or that transmitter transmits X1, okay? And this person has H2 with its own different, now here's the thing, they may be at a different distance, right? They may be, let's say they're farther away from the receiver, so their direct path may be longer. Their bounce paths may be different, right? They may have different bounce angles. Okay, so it could look something like this. But then this, ultimately, this also superimposes here. And now what our receiver sees is the superposition of everything. Okay, because they don't even see, this is very important, they don't even see these intermediate superpositions. They see now 6 paths jumbled together at the same time, and they don't even know which comes from which user. Okay, there we go. So now the equation looks something like, now even here, even in the 1 times 1 case, the user does not know the difference between the direct and 3 paths Actually, a more correct term here is, sorry, it's convolution, right? Let me think here a bit. So it's, yeah, it's convolution between HT, XT, because there are delays. So if you know what a convolution is basically an echo of a sig. It's basically this picture, right? So it's okay, let's write this down better. So YT then will be, it's HT times XT, that's the direct path. But then it's, well, no, we should say H direct, sorry. But it's also plus H path 1 at time t times X of t minus delay 1, okay? So it's a signal from the past, and of course plus the other one, right? Plus dot dot dot, I'm not gonna write, it's H path 2 times X minus delay 2 plus N, okay? So now the same thing happens here, but now it's a superposition of two transmitters at the same time. So it's conv HT, no, H1T, X1T plus conv H2T, X2T. This is a bit harder to estimate now, okay? So when we get to what channel estimation is, it's intuitively, if you think about it, this is gonna cost more. You're gonna have to listen for a longer time to be able to distinguish what two people are simultaneously trying to say to you. So that's why we can say that channel estimation is a bit more expensive here. But you can gain an advantage. Now there's of course also a 3x1 wireless channel, a 4x1, a 1000x1 wireless channel. And in all of these, it seems like the receiver is more and more disadvantaged. And they really are, because when you're trying to listen to two people at the same time, if you listen for like 10 seconds, maybe you'll make out what they're saying. If 3 people are talking at the same time, you're gonna need a lot more time. If 1000 people are trying to speak to you at the same time, you're gonna need a very long time to selectively hear and map out what they say. But you can gain an advantage if you magically have 2 listeners listening to those 2 people, right? So now we can sort of increase the channel in the other direction, which is the final picture we're gonna do. A 2x2 wireless channel. Well, guess what? There's now 2 receivers simultaneously listening to the simultaneous 2 speakers. And that's it. This is, we can also draw this now for 3x3 for 1000 times 600. It doesn't have to be equal, right? You can have 1000 receivers and 500, or 1000 transmitters and 500 receivers. You can have 1000 receivers and 500 transmitters, etc. And the picture here is kind of this. Okay, so let's see. So now, these are the two transmitters talking to the first receiver. So now I have to store H in a matrix. And finally, we understand now why we messed around with matrices, right? So this would be H11. Let's say the convention is and this will be H12. When we read an H times so let's do this convention, right? So Hij is receiver I listening to transmitter J. Okay, so notation is a bit backwards. This is how wireless people like to do it. This is right. So this is H12 because it's the first receiver listening to the second transmitter. It's not H21. It's not the second transmitter transmitting to first receiver. But okay. Now we also have the second transmitter, which you can imagine is another duplication of this. I don't know how to do this. If I could do it in 3D perspective, it would be better. It's sort of in parallel to this, right? But with different coefficients. Okay, so here I can also bend the arrows again. Maybe this second receiver is much closer to the first transmitter. Okay, so they look something like this. Oh no, I should put it here. Oh, I can't. Okay. Oops. Send back. No, I can't send you back. Okay. Oh, I know what's happening here. It's because I'm snapped to it. Okay. And then this has this, but now it's no longer H11. This is H21. So it's the second transmitter listening to the first receiver. And this is H22. And this is Y2. Now, very important, the receiver will simultaneously measure with both the receivers they know what they hear, what each other hear. So now you simultaneously have two measurements, right? So let's see, it's H11, 12, it's H12, 22, H21, and H22, X2. So now estimating channels here. So first of all, it's obvious the channel is a matrix, right? So now we can finally write down the complex channel matrix, right? Which is going to be, let's see if we have a, do we have a big bracket here? Maybe not, we'll have to write it by hand. But then a channel matrix looks something like this. Hang on. Okay. So then we're going to have H11 in the upper left corner. We're going to have H12 because we use the row column convention. We're going to have H21 and we're going to have H22. So this is a snapshot of the matrix at a given time, and it's sort of magically hiding all those delays. Okay, there we go. So this is a MIMO channel matrix, and this is so complex value 2 times 2 MIMO channel matrix at a snapshot in time. Okay, important. This is what we simulated, right? Except we simulated as random Gaussian. Okay, so today let's do some more realistic simulations. Now the other there's one more detail here with the time, but we may actually, we'll probably see that in the toolbox that we're going to use. Okay, so yeah, let's spend today, let's simulate and also let's plot some of these because we want to understand how they look like in relation to each other. Now, of course, the sizes in wireless are much larger. You may already remember from the code that we're talking about like 16 receivers, 64 transmitters, something to that effect. So the nice thing is when you have a lot of these coefficients, you can actually plot it as an image. And we can use color for the magnitude, or we can, because they're complex numbers, we can't really plot complex numbers because they have 2 values in each entry. But if we plot their absolute value, we may see some nice spatial patterns depending on where the receivers are positioned, right? Because some receivers are closer to some transmitters, etc., etc. So there are some nice geometrical patterns. Actually, let's talk about some common patterns in wireless. Well, in wireless, they call these antenna arrays, either transmission, right? So antenna arrays. And they're pretty basic shapes. Like the most basic one is a 1D linear, where all your antennas, either transmitters or receivers, are placed in a single row. Let me take the ... from here. Okay. So this is what you would call a linear equally spaced. Okay, so there's also a spacing parameter here. Okay, obviously this is... So there's a spacing. And then what do we have? Well, obviously we have a 2D grid of antennas with different spacings now in each of the axes, right? So we can take a ... right, something like this. So then we can have a linear 2D equally spaced. Okay, and now the spacing could be different. They could be more spaced in one axis and less spaced in the other. And I think this is it for basics, to be honest. This is what you have on your phone. Like your phone usually has 4 antennas. Depending on who manufactures it, they're spaced in a certain way. Maybe they're, well, maybe this is not true. These days they're probably irregular, right? Of course, we can have irregular receivers or transmitters placed chaotically, but the one thing you don't want to do is you don't want to have 2 antennas too close to each other, because they send sort of redundant information. Both on it's easier to see why on the receiver side. If I have 2 listeners very close to each other, they're gonna hear the same thing, so they don't really gain anything new. You're always better spacing your receivers apart. The dual is also true for transmitters, but there's a bit more math there to understand why, which we can skip for now. It doesn't matter that much. Okay, so this is the basics of how, again, these are complex valued. There's a convolution here, which I kind of glossed over, but you sort of get the idea. We have a system model, right? We have a channel characterizing transmission, and we would like to simulate that channel and learn a generative model for it to simulate, let's say, more data from it. Now, the real reason why we want to learn a generative model is to use it to help us estimate the channel better, but we need to learn a bit more about that. Now, there's 2 ways we could do it, right? We could, let's see, we could look at the formula, okay, which is actually public and in the 3GPP documents. There we go. See, we talked about delays and gains. These are the 2. We have pad powers, delay line cancelers. The formula is definitely somewhere here, right, in the official standards, but it's a kind of a whole beast, right, if you look at it. Now, I'm not saying this could be interesting, to be honest. Let's see, channel model for 5. Where do we see it here? Well, they tell you how to model everything, and it's extremely detailed, right? Yeah, so it's also a 3D model, so it has 3D geometry, not 2D. Very important. There's also a height, which sort of complicates the whole thing. So you have to set your 3 angles for each. They teach you how to transform coordinates, so a lot of trigonometry. Here we go, and then the formulas start, and they never keep ending. Okay. Down tilt, it matters if you're down tilting or up tilting. They give you some scenarios. There's also this, the receivers are not even stationary. They also give you, UT is the user terminal, BS is the base station. So base station is the transmitter in wireless. It's the cell tower, right? User terminal is UT, which is your cell phone, basically, or other device. So they also have mobility, right? Just of the user terminal, obviously, because the tower doesn't move. there's a minimum distance, the UT distribution horizontal, but the mobility part is also a whole different beast, which is insane if you think about it. Like, it's like, you know, the listeners are moving while the transmitters are fixed, so you get very complex channel models. They even have standard office scenarios, again, with spacing between base stations. Exactly. Well, here they even have multiple base stations. Each of these has multiple antennas. Oh, this is one antenna array. This is exactly the 2D grid we drew earlier, right? But there's also polarization of antenna. And then the formulas, they keep on going. They get even, oh, there we go. They get even more complicated. More complicated. There's the line of sight. There's penetration through materials, building. And you end up with these sort of, you know, it keeps on going. You have all these tables, and I think at some point there's, oh, here it is. This is sort of the final formula. So this is the H matrix as a function of time. Actually. That's it. This is sort of what we're trying to do. So we are kind of on the right track, except we would have to implement all of this. And there's even more details. Now, let's not do that, okay? So, although that is good content in itself, it's basically linear algebra. And that's actually, by the way, that's very suitable for GPU processing, because it's a lot of parallelized computations. But that's already been done by a toolbox for NVIDIA called Siona. Okay, so it's an open source library for 6G research. And it's hardware, so it runs on GPUs, and it has 3 components. It has ray tracing, which is really the granular way to simulate these channels. So ray tracing is actually physical simulations. They actually shoot out the rays. This is the same ray tracing you see in gaming, right? Because they shoot out rays and they simulate. The other way to do it is to use Siona Sys, or no, I think it's Phi, which is a link level simulator. Developer guides, tutorials, beginners, differentiable, MIMO, basic MIMO simulations. I think it's in experts. Here it is, MIMO OFDM transmission over the CDL channel model. Okay. But yeah, basically, so what we'll do is we're gonna have to install Siona. We're gonna have to figure out how to simulate channels. And the only thing we care about, the model is standard. It does have some parameters, right? So we'll have to read what the parameters are and which parameters are interesting for us to consider. We don't want to over simulate it. But yeah, so this was just the learning part, right? No coding on this one, but next time we'll dive right into coding. So thanks for watching, if you're watching on the YouTube, and tune in for the next episode.